As the body ages, its ability to maintain cellular homeostasis gradually deteriorates, and one of the most critical systems affected by this decline is autophagy. Autophagy, the process by which cells digest and recycle their own damaged or surplus components, is essential for removing dysfunctional mitochondria, aggregated proteins, and other intracellular waste. In youth, autophagy functions efficiently, protecting cells from oxidative stress, DNA damage, and inflammation. But with advancing age, this system becomes sluggish and less responsive, which has far-reaching consequences for both aging and cancer risk. Reduced autophagic capacity leads to the progressive accumulation of cellular debris and malfunctioning organelles. This buildup creates an environment of chronic low-grade inflammation, often referred to as inflammaging, which is a known contributor to age-related diseases, particularly cancer. Damaged mitochondria are a major source of reactive oxygen species, ROS, which can cause mutations in nuclear and mitochondrial DNA. When autophagy is working properly, these faulty mitochondria are selectively removed through mitophagy. But as this clearance mechanism falters with age, ROS levels rise, leading to genomic instability, a hallmark of cancer initiation. Moreover, senescent cells, which accumulate in aged tissues, are normally targeted and eliminated by immune surveillance and autophagy. When autophagy is impaired, these dysfunctional cells persist and secrete a cocktail of inflammatory cytokines, growth factors, and proteases known as the senescence-associated secretory phenotype, SASP. This secretory profile creates a pro-tumorigenic environment that supports angiogenesis, degrades surrounding tissue barriers, and promotes the proliferation of nearby precancerous cells. In essence, a decline in autophagy not only fails to clean up the mess left by aging cells but also indirectly encourages the formation and expansion of malignant clones. The risk is compounded by the fact that aging is also associated with a diminished immune response, immunosenescence, which limits the body's ability to detect and destroy early-stage tumors. Without effective autophagy to support immune cell function and regulate inflammation, the aged immune system becomes both less vigilant and more erratic, further tipping the balance toward cancer development. Yet despite these dangers, the decline in autophagy with age is not irreversible. Research suggests that certain interventions can partially restore autophagic function in older individuals. Caloric restriction, intermittent fasting, exercise, and compounds like spermidine, resveratrol, and NAD+ precursors have all been shown to activate autophagy in preclinical studies. These strategies not only improve cellular housekeeping but also have the potential to reduce cancer risk by restoring genomic integrity and immune function. However, caution is essential, particularly in individuals with undiagnosed or established cancers, because stimulating autophagy in such cases might also aid tumor survival and growth. This dual-edged nature of autophagy in aging underscores the importance of timing and personalization. In early aging or in pre-disease states, boosting autophagy may help delay functional decline and reduce cancer risk. But in the presence of malignancy, the same intervention could be counterproductive unless carefully managed in a therapeutic context. As we move toward more individualized medicine, future strategies may include autophagy-modulating treatments tailored to a person's biological age, autophagic capacity, and cancer risk profile. In the meantime, understanding that aging and impaired autophagy are tightly linked provides an important framework for disease prevention. The more we learn to support this critical cellular process, without tipping it in the wrong direction, the better equipped we will be to manage not just aging itself, but the diseases that most commonly follow in its wake.